Okay, so what we're going to talk about today is 16.5, which is curl and divergence. And the reason that we're going to spend time on, more time than the book probably spends on what these things mean, is because I want to teach you what I think is the true version of Green's theorem. So last time we talked about in 16.4, I stated Green's theorem. Green's theorem is stated over some simple region D with a boundary C, and the theorem itself says that the integral around C of p dx plus q dy is equal to the double integral over D of dq dx minus dp dy dA. And I guess probably a more proper notation for this would be the integral around C plus of f dot dr, right? That's the sort of more proper, it's a line integral, right? You're computing work with this. And so one thing I didn't talk about yesterday was what this means. I sort of mentioned maybe that it involves something about a twisting of a vector field or rotation of a vector field. We're going to talk about different vector operations today that will give us, I think, enough physical intuition to know why Green even came up with this theorem in the first place, and why you should believe that these two things are equal to each other. And we're going to start with some vector operations. So we're going to define a quantity called the del operator. This is sort of a notational convention, and it's a function that eats functions and then takes derivatives. So it's a vector. Del is the vector, derivative with respect to x, derivative with respect to y, derivative with respect to z. You should think of this as a function that's looking around looking for things to eat. We've already seen an example of what the del operator does because we use this to define the gradient. So the gradient of f, gradient of some scalar function f, we wrote down the symbol grad f for that, del f. And if I'm thinking about this as a vector operation, d by dx, d by dy, d by dz, times a scalar function f, if this was a vector times a scalar, the way that you take a vector and you multiply it by a scalar is you just put the scalar inside with all the components. You entry-wise multiply the scalar into the vector. So the vector operation of scalar multiplication would say, take the f and multiply each of the inside components by that. D by dx of f, d by dy of f, d by dz of f, which is f with respect to x, f with respect to y, f with respect to z. Scalar multiplication of vectors, one of the multiplication operators for vectors, gives us a formula that allows us to apply the del operator to a scalar function f. And the idea is all of the other vector multiplications also give us meaningful calculations. So with vectors, I have 3 vector multiplications. I have scalar multiplication, just the gradient of f, which is equal to fx, fy, fz. And I have 2 more. I could take a cross product. That's another mathematical operation I can do with vectors. That's a multiplicative operation. So if I want to take a cross product of del with something, it had better be a vector. So I can think of this as d by dx, d by dy, d by dz, crossed with a vector field p, q, and r. Remember, cross products only make sense in R3. And we also have dot products. So the dot product, I could take the del operator and I could dot it with a vector field. And that would give me d by dx, d by dy, d by dz, dotted with p, q, and r. So we're going to start by looking at this one. We're going to spend some time talking about this sort of formal cross product that I've set up. And then we're going to come back and we're going to see how that quantity gives us a new way to interpret what Green's theorem says. Okay, so definition. Given a vector field f of functions p, q, and r, the curl of f is curl f equals del cross f. So, without physically motivating it, I'm going to tell you how to compute it. Curl is a word that's chosen for a reason, because this is picking something up about rotation of vector fields. If I wanted to compute this using what we already know about how to compute cross products, the way that I would actually compute this would be, okay, so del cross f should be equal to, in fact, let's just do an example. And then I'll give you the formal definition in a second here. So del cross, given a vector field f is equal to y minus x, 0. There's a vector field. And I want to compute its curl. What the formula says to do is to calculate the curl of f, I am going to take the del operator and cross it with f, which is d by dx, d by dy, d by dz, crossed with y minus x, 0. And I know how to compute cross products. I'm going to use that determinant formula. Now this is kind of the ultimate abusive notation here. This is the determinant of I, j, and k. So the first row of this calculation is unit vectors. The second row of the calculation is this vector, which is made up of derivative operators. And the third row is the thing I'm actually trying to compute the curl of. Y minus x, 0. So you should think about this as just a way of arranging a calculation so that the answer turns out to be correct. It's a way of storing how the calculation works. The way that we calculate the determinant of a 3 by 3 matrix, or a cross product, if you remember from when we were doing vector operations back at the end of 143, is this is going to be I times the determinant of the matrix that's d by dy, d by dz, minus x, 0, minus j times the determinant of the matrix that's d by dx, that's not a 2, d by dz, d by dz, y, and 0, plus k times the determinant of d by dx, d by dy, and y, and minus x. Other than the notation, we've already done a bunch of calculating cross products with that. The difference is, when I multiply here, I'm actually taking derivatives. That's what this step is supposed to be implying. If I'm going to multiply d by dy by 0, that says take the y derivative of the 0 function. That says take the z derivative of the y function, or the x derivative of the x function. We're applying the derivatives as I calculate the curl vector here. So if I was going to continue with this, I would get d by dy of 0, which is 0, minus d by dz of negative x, which is 0, minus j times d by dx of 0, which is 0, minus d by dz of y, which is 0, plus k times d by dx of negative x, which is negative 1, minus d by dy of y, which is 1. And so all of this turns into the vector 0, 0, negative 2. The curl of a vector field is a vector. Now, what does that vector mean? I guess the first thing I should do is tell you what the general formula is, and then we'll try to interpret it. The general formula for the curl of a vector field, so del cross F, which is del cross PQR, has the general formula if you work through the determinant calculation. I don't memorize this. I just know how to take the cross product. So you can memorize this, but you don't need to. dr dy minus dq dz in the I direction plus dp dz minus dr dx in the j direction plus dq dx minus dp dy in the k direction. And that should all, right there it is. That quantity right there that shows up in the calculation of the curl of a vector field is this quantity. So if you calculated this using the determinant formula, this is the formula that would come out. And this quantity right here in that calculation is this quantity. So somehow this thing that I've built, this curl function, is showing up as a quantity in Green's theorem. So what I try to do now is convince you something about what the curl is actually doing, what it's measuring, why we even named it curl. So I'm going to look at just this part, and we're going to try to figure out what this means. Why are we calling that curl? So what does dq dx minus dp dy measure? So I want you to imagine that you've got some vector field floating around, and in that vector field you take a particular point and you attach a little like a pinwheel to it, a wheel that can be turned by water, say. You've got a bunch of water flowing around, and in that field of water, you stick a pinwheel down. And I would like to know, subject to the forces induced by that vector field, how that wheel wants to turn. Does it want to turn clockwise, counterclockwise? How much does it want to turn, and and how much, right? What's the magnitude of its tendency to turn? So what I'm going to do is I'm going to look at the difference in forces that happen on two of the sides. So you can imagine here, this is sitting inside of a vector field. The force field is acting in that direction. And if I want to know if the force on this branch of the pinwheel make it turn, I should look at this bit of the force vector F on this end of the arm, and then this bit on this side. Notice that this is the component Q of the vector field, and this is the component Q over here. Q is the point that is the component of the vector field in the y direction. F here is equal to P comma Q. Q tells you how much of the force points in the y direction. In the picture that I've drawn, what direction does that wheel want to rotate? Clockwise or counterclockwise?
Clockwise.
There's an axis here, so it's going to spin like a wheel. It's going to turn this way or it's going to turn that way. More force on the right side means that it wants to turn this way, right? At least if you drew this. Now, one way of measuring if this vector is larger than that one or smaller would be to say, well, if I'm at this point right here, x, y, and then I slide over here and I look at the point x plus delta xy, I could measure the change in the q vector as I move in the x direction. The difference between these two vectors, the difference in size here, can be measured with change in q divided by a change in x. If that quantity is positive, it means that vector got bigger as I move to the right. If this quantity is negative, it means the vector got smaller. So if dq dx is positive, like it is here, the vector started small and got bigger, so change in q is positive, then the wheel wants to rotate, then you have a rotation, a tendency to rotate. So a rotation tendency in this case, in the counterclockwise direction. It wants to go this way, at least according to the way that I've written the forces down, right? dq dx being positive means this wheel wants to go this way. Now that's not the only force acting on my pinwheel. I have forces that are acting in this direction on these two branches as well. So I could say, well, what's going to happen there? Let's look at the force vector here, F, and we'll go up here and look at a different one. And if I want to measure how much the wheel is being induced to turn with respect to this set of fins, I could look at this vector, which is the vector P, and I could look at this vector, which is a different vector P. And I could look at that point, which is located at xy, and slide up here and look at the point xy plus delta y and say, hey, if I move a little bit in the y direction, what is the change in size of this p vector? If I look at dp dy, in this case, I guess this is also positive, right? So now the wheel wants to turn this way. This vector is supposed to be slightly longer than that one. So if p dy was positive, now we have a tendency to rotate in the clockwise direction. If that vector was bigger than this one, the wheel wants to go this direction. So these two things being positive act opposite each other. Positive change in q with respect to x wants to turn the wheel counterclockwise. Positive change in p with respect to y wants to turn the wheel clockwise. If I want to measure the net force on the wheel, I subtract. That's tendency to rotate as I slide in the horizontal direction. This is tendency to rotate as I slide in the vertical direction. I subtract to get the net tendency to rotate. And so that's exactly what this is measuring. Tendency to rotate at a point in 2 dimensions by looking at the decomposition of the vector field into its horizontal components and its vertical components. And that's exactly why we call this curl. Curl is a way of measuring local rotation. Now, admittedly, to prove this, that this picture is accurate, takes more math than I have available to show you guys. But I think that this is where the original idea for curl came from, was I need some way that I can look at the tendency of a vector field to swirl locally. Okay, so if you buy that, if you buy that this measures tendency of a wheel to rotate, the next question you might have is, well, why are there 3 terms here? In the 3D case, why are there 3 terms? And the answer is, this term measures how much the vector field wants to rotate around the z-axis. This term measures how much the vector field wants to rotate around the x-axis. And this measures how much it wants to rotate around the y-axis. So the total rotation is the sum of the tendencies to rotate on the 3 coordinate axes. So that's kind of what the curl vector does. It stores 2 pieces of information. The first piece of information it holds is how much rotation should be happening. This corresponds with angular momentum if you've seen that in a class before. And the direction that this vector points actually tells you the axis that you would rotate around. Okay, so with all of that said, what the hell is Green's theorem actually telling you? First off, any questions about this picture? Admittedly vague, but hopefully indicating about what this mysterious quantity is actually doing. Yo.
I just had a question about the equation in the bottom left. How did you get those, what did the cross product?
Oh, okay. Well, let's actually just write it down. So del cross PQR is equal to the determinant of I, J, K, d by dx, d by dy, d by dz, p, q, r. And that's, so now it's I times the determinant of d by dx, d by dy, d by dz of q and r. And then there's more stuff, but then that means that you get out dr dy minus dq dz.
Okay, that makes sense.
Right? It just comes from just running through the typical calculation for a cross product. It's like if you write this down from the definition and you actually do the calculation, this is what falls out of taking that determinant.
Okay.
Yep.
I had a question. For delta p over delta y, why is, like, when you say it's greater than 0, why is the rotation clockwise and not counterclockwise, like the change of q over change of x example?
Do I have this backwards? Because this is the, so if I make p, so I'm going to really exaggerate this. If I have a pinwheel and I have a little tiny vector down here and a great big huge one up here,
Yeah.
right? The change in this vector is positive, right? It was started small and got bigger. Which way does the wheel want to turn? It wants to turn this way, which is clockwise.
Okay.
That's how a clock turns, right?
That clock turns.
That's exactly, you know, there's you should trust me that that's the way that the clock turns, right? It goes that way.
It's because intuitively I didn't get it at first, but then I now realize, yeah.
Okay. Okay, so let's actually look at what Green's theorem actually says then, and which I think is, this is why Green himself, who was interested in the flow of vector fields and the flow of fluids, actually invented this stuff. So he sees dq dx minus dp dy and says, okay, that's tendency to rotate in the plane, but the definition of curl is a three-dimensional definition. So, and it's always the case that the term that I want here is in the third spot, right? That term in Green's theorem is in the third spot of the definition of curl. So I'm going to cheat, and I'm going to say, if I took the curl of f, which is equal to some stuff I'm not going to care about, some stuff I'm not going to care about, and dq dx minus dp dy. And I really just want that quantity. I don't care what's here and here for Green's theorem. If I just want to extract that piece of information, what I could do is I could take that vector and I could dot it with the vector k. I could take something I don't care about, something I don't care about, dq dx minus dp dy. And if I just want that bit of information, if I dot this with the vector 0, 0, 1, the only thing that survives is the term that I want. 0 times the first term plus 0 times the second term plus 1 times the third term gets you dq dx minus dp dy. So a calculational trick is just to notice that I could write the curl of f and then dot it with the unit vector pointing in the z direction. I would get exactly the term that I wanted from Green's theorem. So Green's version of Green's theorem, what I think is the true version of Green's theorem, says that the integral around the boundary of f dot ds is equal to the double integral on the interior of the curl of f dA. This is what I think of as the true version of Green's theorem. And there's nothing has happened here except for a notational change. It's the same theorem. But the interpretation of it turns out to be really different. So all I've done here is replace p dx plus q dy with its work integral form. And I've replaced this dq dx minus dp dy, this sort of weird calculation, with an actual explicitly acknowledging that what I'm calculating is something about the tendency of the vector field to rotate. And now I should be able to convince you something about why Green's theorem is actually true. Like what Green's theorem is actually saying. What's up, Aaron?
If you dotted the cross product with another unit vector, would that give you any meaningful quantity?
Yeah, so if you dotted this with the I vector, you would be picking up tendency to rotate around the x-axis instead of the z-axis. So essentially what we're doing is we're pretending for a second that our two-dimensional vector field, so we're imagining that our two-dimensional vector field just lives in the xy plane, right? So we say, oh, well, if the vector field just does whatever it does in the xy plane and the z doesn't matter, well, that's what we're sort of cheating and pretending we're looking at the vector field f is equal to pq0. And if we have pq0, it will turn out to be the case that the curl of f will be equal to 0, 0, dq dx minus dp dy. And I just want to dot, I don't need the vector, I just need that number, so I dot it out. So a 2D vector field can always be, you can sort of cheat and put it in 3D by sticking a 0 in the third slot. the pretty typical trick. So yeah, if you took a general vector field and you dotted it with the I vector, you'd be picking out tendency to rotate around the x-axis. But because this is living in the xy plane, there is no tendency to rotate around the x-axis. It's the same everywhere in the z direction. So it's sort of a flow that's going all this way. It's a good question. Okay, so now I'm going to try to, if you buy that measures curl, and that there's a way to measure curl, I'm going to try to convince you what Green's theorem is actually saying. So imagine I give you a really simple version of a domain for a second for the sake of argument. So this is your region D. It's a rectangle. And the boundary of D is the outside of the rectangle, oriented positively. That's your curve C+. So here's what Green's theorem says. If you could cut this all up into little bits. In fact, I can tell you, I'll even make this more concrete. I came up with this last class. You just imagine it's a swimming pool full of water, rectangular swimming pool. And there's a whole bunch of people in the pool. Those are the pinwheels. And they're doing things, right? Spinning around or whatever. They're moving their arms, they're sloshing around. If you could measure at every point in the pool how much rotation is happening at each point, so if every spot in the pool you could calculate how much tendency to rotate is happening, and you added those all up, everybody's individual contribution to the movement of the pool, of the water in the pool, so if you summed up all the curl, so if you add up a bunch of curl, what you're going to get is the way the water is moving at the edge of the pool. Just imagine a bunch of people, you've probably all done this, you get in a swimming pool and a bunch of people go in a circle and it sets up a whirlpool, right? So everyone's in the pool stomping around like, they're moving in a way that sets up the fluid moving around the edge. You could do that likewise if you had people move, just a bunch of people stationarily moving and spinning the water. The sum of the effect of everybody churning the water is going to induce some sort of movement around the edge. So what Green's theorem is telling you is, if you add up all the curls on the inside, all of the local tendencies to rotate, what you can say it must be equal to is the total circulation of the water on the outside of the pool. The total tendency to rotate in the interior is equal to the total circulation on the outside. That is what Green's theorem is actually telling you. It's a theorem of fluid dynamics, ultimately, or electromagnetics. The work done on the edge, the circulation integral, is equal to the sum of the rotations in the interior. So you can imagine, if nothing is rotating in the interior, if people are just going back and forth like this, right? They're sort of sloshing the pool this way. Nothing rotates. There is no circulation on the boundary. No rotation in the interior means no motion on the boundary. You get like slop going this way. If everybody starts sort of going back and forth this way without rotating, you'll get motion this way in the pool, but no net circulation around the edge. If everybody starts to spin randomly, depending on how they spin, the average contribution of everybody's spinnings, if two people are spinning opposite directions, they cancel. If they're spinning the same direction, together, they might contribute. Their rotations are going to contribute to a rotation. So on average, the sum of the average rotations is equal to how the water is going around in the edge. So this is kind of like a core idea in applied mathematics and physics, is to relate different quantities on the interior of a region to the exterior. So I think of this, even though this is nothing more than a notational change, I think of this as sort of the correct version of Green's theorem. And the reason that you might think about it as the correct version of the Green's theorem is, this is the one that we're going to be able to turn into a theorem in 3 dimensions. This does not lift to 3 dimensions in a natural way. That absolutely does. This turns into something called Stokes' theorem, if you've seen that in a class before, which is kind of like, this is what we're driving at, is really like to show you guys Stokes' theorem. Okay, so if you buy this picture about rotation, that's the way I even remember Green's theorem. I don't remember Green's theorem except like, okay, what am I actually doing? A circulation on the boundary is equal to the sum of the rotations in the interior. I don't need to memorize the theorem because I know the principle. Yep.
Is it always with work then?
So it's not always with work because you can interpret this circulation integral in different ways. You could actually interpret this as like net flow of water or net change in volume or something like that. So it's the units that you set the problem up in dictate different applications of this. It's that the mathematical theorem was discovered and motivated by the fact that this was a work integral. So this applies in context where it's not actually work. But the easiest way to remember the theorem and why it even should be true, I think, is with its original motivation, which was in terms of work. All right, so we have one more vector operation to discuss, which actually gives a different version of Green's theorem. So we left off one type of vector multiplication. What have we not done yet? Dot product. Okay. So if I took the del operator and I dotted it with a vector field. So when mathematicians don't know what they're doing, they just say they're proceeding formally. So we're just going to proceed formally and then hope that we can interpret the thing that comes out the other side. I'm just going to do it. Del dot f is equal to d by dx, d by dy, d by dz, and I'm going to take the dot product with the vector field p, q, r. So the dot product says you're supposed to multiply all the entries and then add them up, right? So this turns into dp dx plus dq dy plus dr dz. So I told you nothing about what this measures. I will though. Nor what it's called. So this actually turns out to be called the divergence of f. And the short name for this is div. So the divergence of f is del dot f. And just like with how curl measures rotation by looking at change in a vector field locally on a pinwheel, I can draw a similar sort of vaguely hand-wavy but justifying picture for what the hell this is actually doing. So in applications, when you're working with vector fields in practice, you have two different sorts of scenarios that show up routinely in vector fields you like to be able to describe mathematically. A vector field can have a place called a source, which is a place where it seems like the vector field emerges from. And I'll say emerges. So what I mean is, if you think about an electron inducing an electric field, here goes a picture you see in every physics book, right? And there's these lines that come out that look like this, like, you know, the electric field gets weaker as it gets out. But, I mean, I guarantee that if you've taken this class and your physics has this picture inside of it, right? Like, oh, it's a point charge in the plane. Here's what its vector field looks like, right? One way of knowing that the vector field came from that electron mathematically would be to say, if you drew a little box around it, and then you calculated something about the amount of vector field that was leaving through the boundary of the box on net, a positive amount of stuff is leaving the box through the boundary. It's going from the inside to the outside. The vector field is being created inside the box. A net amount of stuff is, if you imagine like, this is measuring fluid flowing. If there was a faucet here, the faucet is creating liquid in the system. So it's a source because the stuff is emerging and passing through this boundary, and I could measure that amount of vector field passing through the boundary by giving it a name. Oh, I call it divergence. So we call this the divergence of f would be positive at that point because stuff that on net, more stuff is leaving the interior of the box than is coming into it. I also have scenarios in the opposite scenario, or the opposite case. So I could put a proton down here, and then I've got vector field that's approaching. You know, this is sort of a typical kind of picture, is you have vector field that's all coming in, all points in. If you drew a little box around that guy, now nothing is leaving the box and everything is coming into it. In the literature, this is called a sink. You can think of drain in a fluid problem, right? That's a place where water is leaving the system. The vector field is entering there and not coming back out again, like a black hole. So this is where the vector field is on net entering the box, and on balance, like more stuff is coming in than leaving. So we call this divergence of F negative. And then the third scenario would look something like this. I could have a box. This is something that shows up in. I'm gonna hit you with a physics word here. If I have what's called a laminar flow, you can think about that as looking like this. So it's linear, equal velocity. What's the divergence of the box now? If you think about net fluid in versus fluid out, this is 0. It's the same, right? So the net change or whatever of the vector field passing through the boundary of the box here is 0. So you would call this a divergence of F being equal to 0. I will point out that in practice, for those of you that have seen this, divergence of F, if the divergence of a vector field is 0 everywhere, it's called incompressible. So water is usually modeled as an incompressible fluid. So divergence-free vector fields. Gases are compressible. So oftentimes when you're studying gas, you do have regions where they squish together, and you might have more vector field squishing in than leaving. Okay. So what on earth does that picture that I drew right there have to do with this? So let's look at just the 2D case. Divergence, unlike curl, always makes sense for any number of dimensions. And so if I just had F was equal to a vector field PQ, I can still define the divergence of F to be dp dx plus dq dy. So I'm going to imagine that I'm going to point at the plane, and I surround myself with a little box, and I say, I sure would like to know the net flow of fluid through that box in and out. Like, how much goes through the boundary? So the way to measure that is you say, well, if I had an F right here, and I slid over to the edge and looked at the new F, what I'd be looking at is, well, there's an amount of vector P here, and the amount that passes out of the box is in that same direction, perpendicular to the edge of the box, right? The way to measure the amount of fluid passing through the boundary of the box would be to say, well, over here it was only going that fast, and over here it's going this fast. Or the quantity that was being, passing through, forced by the vector field here is this version of P, and I get to the edge and the P vector has gotten bigger. So the net change in P has increased. So if you look at the distance, or the difference between this vector and this one, you could call that change in the P vector. And since we slid in the horizontal direction this time, I'm going to take that with respect to change in x. That is going to tell us something about the net change from this edge of the box to that one. More vector field, if this is positive, it would say more vector field is emerging in this direction than came in from this one. So this would be a picture where dp dx is positive. Why doesn't q matter? I mean, after all, I have a vector q right here. And that vector q is right here. Why doesn't q contribute to thinking about the amount of fluid passing through the edge of the box? There's no change in y, right? It's parallel to the edge that it's passing through. Change in q doesn't tell you anything about the amount of fluid that's passing through this face of the box. On the other hand, if I looked at this vector up here, I could pick a different f, like this one, and I looked at its q vector. Now you can imagine, look, the amount that passed in was equal to this, the amount that passed out is equal to that. Now I do have a change in q. Going in this direction tells me something about the relationship between what passed in this side and what leaves through that one. So if I want to figure out what's happening on this edge, between these two edges, I could look at dq dy. And now notice, unlike the case with rotation, these carry the same sign. They both induce positive. If these guys are both positive, it means more stuff is leaving than is coming in. So So if I want to know the total amount of net change inside the box, you just add them together, and that's what this is doing. You're adding up the net change through the faces that are parallel to the x-axis, plus the net change of the faces that are parallel to the y-axis, plus the net or perpendicular to the y-axis, plus net change to the faces that are perpendicular to the z-axis. So this is just the cube picture. So physically, what divergence is doing is telling you something about. Say, I'll do the cube. I have a certain amount of vector field coming into the bottom and a certain amount of vector field leaving. And if I want to measure how much that changes, I could look at dr, dz. Changes in the r vectors as I slide in the z direction. That's what that picks up. If I'm moving in the y direction, that would say, okay, coming through this face, I have this vector coming in and that vector going out. These are q vectors. If I want to know what the net difference is between the amount of stuff coming in and the amount of stuff leaving, I could look at dq, dy. If I'm coming in this x direction, I'm looking at vectors that are sort of doing that. These are the p vectors. I could look at dp, dx. So the net effect on the entire box can be decomposed into the bit along the x-axis, the bit along the y, the bit along the z. Now you might have the question, how come you only have to check 3 directions to make this make sense instead of all the possible directions? And the answer is, as long as everything is differentiable, this works. Differentiability means that you can decompose something into coordinate directions, and this is a sensible thing to do. All right. So now my question is, let's actually calculate a divergence. And then we'll try to interpret the result that we get. So we already looked at the vector field f was equal to y minus x 0. And we already calculated that the curl of f turned out to be 0, 0, negative 2. Let's look at the divergence of f. So the divergence of f is del dotted with f, which is d by dx, d by dy, d by dz, dotted with y minus x 0. And this is going to be d by dx of y plus d by dy of minus x plus d by dz of 0, which is 0. So this is a divergence-free vector field. So it has curl, but no divergence. Let's draw a picture and see if we buy that. So I'm just going to look at the 2D version of this. You have x, you have y. This particular vector field has arrows that increase in size the further away you get from the origin. The vector field y minus x 0, I think, so if you're at the point 1, 0, then you introduce the vector 0, 1. If you're at the point 1, 1, you're the vector, what is 1, 1, or 1, what does 1, 1 do? 1 minus 1? Am I doing this right? What does 1 minus 1 spit out? What does 1, 1 spit out? 1 minus 1. Okay, so 1 in this direction, then down. Okay, so it does this. That's weird. What does 1, 2 do? 1, 2 spits out the vector 2 minus 1. So it's 2. So it's like, oh man, I took totally a wrong picture in the last class. Okay, how about what does 1 minus 1 spit out?
Minus 1.
1 minus 1 turns into
Minus 1.
minus 1, minus 1, minus 1.
Yeah.
Oh, okay. Yeah.
How about this point right here? How about 1, negative 2?
Negative 2, negative 1.
Negative 2, negative 1. Wow. What happens? What about 0, 0?
0.
How about 2, 0?
0.
0,
Zero, negative 2.
For 1, 0 wouldn't it be 0?
Is this negative? Did it go this way?
Yeah.
Oh, okay. That's why I'm so confused. Okay, my bad. All right. So 0, negative 2, and then is this just a rotational one? What happens at 0, 1? 1, 0. And what happens at 0, 2? 2, 0. So is this our typical sort of like things are rotating like this? Wow, I did not draw the wrong picture. Okay, so I thought I was wrong, but I was right. Okay, so I guess the idea here to think is that these vectors start small and they get bigger in a linear way, right? On any line like that, the vectors are all parallel to each other, and the further away from the origin you get, the larger they get. So what I would imagine is, if I drew a little box in here to calculate the divergence, and you think about the vectors that are coming into that box, notice for a small enough box, these look like they're entering all parallel to each other, and they're leaving all parallel to each other as well. And at least squished in this way, I guess the idea here is the divergence is telling you the amount of fluid flowing through this box, net in and out, is equal. That's what the divergence is telling you. No matter where you put the box, if you put it over here, the same thing is going to be true. You're going to have a bunch of sort of circular flows that are entering, but they're also leaving in a corresponding way through the other side of the box. So the net divergence being 0 means everything that you put, no matter where you locate this box, the amount of fluid flowing in and the amount of fluid flowing out are equal. So that's kind of what divergence 0 would mean. Why is there a curl in this vector field? Why should that be true? So if I put a pinwheel down right here, and I ask, why is that wheel rotating? Because it is. I mean, this says the wheel is rotating. It even tells me what direction it's rotating. It's negative. So if it's negative 2, that means it tells me that it's rotating in a clockwise direction. Why would we believe that the wheel is rotating in a clockwise direction here? Like, what should be happening?
Because they get bigger the further away.
If you think about, the forces that are acting on the arms here, this side is closer to the origin and so has smaller forces acting on it than that side of the pinwheel does. If you imagine making a line right here, the forces that are acting on those branches is higher than the forces that are acting on these, because they're further away. And that means that the wheel wants to turn this way. And no matter where you put the wheel, it wants to turn. So this is a field where no matter where you stick your pinwheel, this part of the pinwheel is under more force than this part is, because the vectors get bigger the further out you get. Is it possible for a vector field to have local curl without rotating? So what I mean is, this is a rotating vector field, right? The whole vector field, it's turning in circles. Could I come up with a vector field that has local rotation but not global rotation? How would I do it? I want a vector field that does not look like anything should be rotating, but is. Yep.
Wouldn't you have the example of two people rotating opposite directions in a pool? Wouldn't that create the same effect?
I have an easier example. I can make a vector field where all the lines are parallel to each other. All the flow is parallel, and yet there is still rotation. So you can imagine that if you had a vector field that was set up like this, where maybe the vectors down here are all small vectors, and then as you get further up in the y variable, the velocity gets higher. The further away from the axis you get, the more velocity there is, right? And you can imagine that if you stuck a pinwheel into here, this is under much higher force than this is, because even though these things are all linear, right, the vector field itself is a linear flow, but the scale is not constant. It's not a constant flow. And so this is one where you will induce rotation in this direction, because the further away from the origin you are, the larger the vector field is. So these sort of analyzing vector fields can be really complicated, actually. Okay, so next time what I want to talk about is the divergence version of Green's theorem. You might be able to anticipate what that should say. And then we'll move on to talk about parametric surfaces. My goal is I really want to talk about the Stokes theorem, which is basically Green's theorem in 3D.